Tonight, what we're going to be talking about is solving systems of equations by elimination. Yesterday, we discussed that to solve a system of equations, what you're looking for is the point of intersection. And that's great. Graphing is a fantastic way to find that point of intersection. However, it is not always the most accurate, especially when we're graphing by hand. If we're graphing by hand and we don't draw our line completely straight, or if it doesn't cross at an exact point on the graph and we're trying to estimate what the answer is. It's great with graphing tools that can give us that answer right away. However, we know graphing tools aren't always available to us. And so we need to have a method that we can solve systems of equations without having to use some kind of graphing tool, but that will get us the exact answer, and we're not just estimating it off of a hand-drawn graph. And so we do have a couple of algebraic ways that we can use to solve systems of equation. And today we want to talk about elimination as one of those methods. So the problem with a system of equations is that we have two variables. So there's two things that we don't know. I know how to solve an equation and solve for one variable, but I don't know how to take an equation with two variables in it and figure out what they both are. It does require two equations. So now that I have two equations, the problem is I still have two variables, and now I have two equations, and I don't know what to do with that. If there was some way that I could get rid of one of these variables and only be left with one variable, I would know how to solve that equation. One equation with one variable, I know how to solve that. And so what we start noticing is we just need to keep in mind, our problem is we needed one equation with one variable, and if we have one equation with one variable, we know how to solve it. So if that's what we want to have, how can we make that happen? So what we want to remember is the power of the equal sign. When things are equal, we know they are the exact same thing. We know that we can balance equations. If I add the same thing to this side of the equation that I add to this side of the equation, as long as I'm adding the same thing, then I know that the equation is still balanced, it's still equal. If I know that two things are equal to each other, then I know that they are the same thing. And so when we realize that, I look at these two equations and I think, well, if I actually were to add these equations together, take this side and add it to this side, and take this side and add it to this side, I would not have changed the equation any, because these two are the same thing. They're equal. So as long as they're equal, I'm adding the same thing to both sides, then these are still going to be equal. And you're like, well, that's interesting, Ms. Parker, but what would be the point of that? Why would we want to add the two equations together? Well, we don't want to add them together in any random way, but if there was a way that we could add them together so that one of the variables went away, I could eliminate the x's or I could eliminate the y's. If there's some variable I can get rid of, there would be an advantage to adding them together. So when I look at this equation, if I were to take these two equations and add them together, I have x plus x, which would be 2x, but I have 1y and negative 1y. 1y plus negative 1y cancels out. It eliminated the y's. I have my equal sign, and then on this side I have 10 plus 8, which is 18. What just happened is I added these two equations together, and now I have one equation with one variable. This is 2x equals 8. All I need to do now to solve for x is to divide both sides by 2. And I actually end up with that x is equal to 9. Now, if you remember, the solution to a system of equations is a point. So this gives me 9, however, I am missing the y value of my point. So I do need to take this value back up to the original problem here and plug it in for x. So 9 plus y is equal to 10. And so that is one equation with one variable. I know how to solve those. I can subtract 9 from both sides, and y is going to be equal to 1. So sometimes you will see this referred to as the addition method, the addition and subtraction method. You also hear it referred to as elimination because we're getting rid of one of the variables. So the idea here is that you want to add the two equations so that one of the variables is going to disappear. Now, in this case, the equation was already set up so that the y's were opposite of each other. Obviously, that doesn't always work out that way. So you may have, for example, something like 3x plus y is equal to 5, and 6x plus 2y is equal to 10. And this is our system of equations. So right now, I don't have anything that's opposite of each other. And so adding these together would still give me one equation with two variables in it, and that's not going to do me any good. So sometimes we have to play with the equations a little bit in order to make them opposites of each other. So when I look here, I'm like, well, this is just plain old y. But if it was negative 2y, negative 2 plus positive 2 would be 0, and the y's would go away. Or I look at the x's and I say, oh, this is 6x, and this is 3x. But if this was negative 6x, then I could add them together, and they would cancel out. All right? So sometimes we have to manipulate the equations a little bit. So I think, how could I make this be negative 2y? Well, I could multiply it by negative 2. The thing we have to remember is that if we multiply one part of an equation by a number, we have to distribute it and multiply the entire equation by negative 2. So I want to take this negative 2 and I want to distribute it to all three of these. So that's going to become negative 6x plus negative 2y is equal to negative 10. And then the bottom equation was 6x plus 2y is equal to 10. Now when I add these equations, look what happens. Negative 6x plus positive 6x cancels out. That's just 0. Negative 2y and positive 2y also cancels out, which is just going to be 0. I've got my equal sign, and negative 10 plus 10 is equal to 0. So I actually ended up with 0 equals 0. Now you may think, Ms. Parker, we've done something horribly wrong. No. If you remember yesterday, not all of the systems of equations had solutions. Sometimes we had parallel lines or coincidental lines, and we got infinite solutions or no solutions. That's still going to be the case. We just weren't graphing this so it didn't jump out at us and say, oh, those are parallel lines. They weren't in y equals form, so I didn't see whether or not they had the same slope. So how can we tell whether it's parallel lines and no solution, or if it's coincidental lines, the ones that are right on top of each other, the dependent system, and has infinite solutions? Anytime your x's and your y's both cancel out, it means that they're either going to be the same line or they're going to be parallel. Here's how you can tell. Look at what is left. If what is left is a true statement, that means that they are the same line. If what is left is a false statement, it means that they are parallel and there is no solution. So when I look at what's left here, I got that 0 equals 0. That is very much a true statement. Yes, 0 does equal 0. That means that this is a problem that has infinite solutions. They're the same line. Another hint to that was when we multiplied, notice that everything ended up being the opposite. It was 6, negative 6, 2, negative 2, 10, negative 10. They were the exact same equation. And so that means that this one has infinite solutions. But the idea here is to eliminate, sometimes you have to multiply by a number. Another example. If we look at 5x minus 3y is equal to negative 18, and x minus 6y is equal to negative 9. So when I look at this problem, I try to see what could I get rid of. Well, nothing is opposite of each other right now. This is 5 and 1, negative 3 and negative 6. So nothing's canceling out right now. But I do notice this is x, so it's easiest to multiply by something and make it opposite. So if this is positive 5, I need this to be negative 5. So I want to multiply everything by negative 5. So the first equation I'm not changing. It's going to be 5x minus 3y equals negative 18. But I'm going to distribute negative 5. So this is going to be negative 5x. Negative times negative is going to be positive 30y. And negative times negative is going to be positive 45. So then, when I add these two, 5x and negative 5x cancels out. It eliminates. Negative 3y plus 30y is going to be 27y. Equals, stays the same. Negative 18 plus 45 is going to be 27. So this is an equation that I can now solve. I have one variable and one equation. To get the y by itself, all I have to do is divide by 27. So y is equal to 1. Again, we want to remember that's just 1/2 of a point though. That's my y coordinate. I still have to find my x coordinate. So go back to the original problem and plug y into one of them. Here's the good news, folks. It doesn't matter which one you use. So you can choose either one. I'm going to choose this bottom one and say x minus 6 times 1 is equal to negative 9. X is, let's see, that'll be negative 6. So if I add 6 to both sides, x is equal to negative 3. So the point negative 3, 1 is the point of intersection for these equations. Now sometimes they like to be complicated and just have nothing that matches. For example, if I've got 3x plus 2y is equal to negative 1 and 4x minus 5y is equal to negative 32, how would I solve this one? I can still use elimination, but not right away. Because notice, 3 and 4, they're not opposites of each other. 2 and 5, they're not opposites of each other. I can't think of anything right off the top of my head to multiply 3 by to make it equal 4, or 2 by to make it equal 5. So sometimes you do actually have to multiply both equations in order to make a variable be opposite of each other. What's cool is this will always work. The other ones, we just got lucky. We were able to cheat and just multiply one equation, or in the first one, we didn't even have to actually multiply any of them. However, this method will always work. If you don't have anything that's opposite of each other right away, or something that you can easily get to be opposite of each other, the one rule that always works is to multiply one equation by the coefficient of what you're trying to get rid of in the other. And then multiply this one by the opposite of the other one. So before we get too lost, first we need to pick a variable to get rid of. Doesn't matter which one. I'm going to get rid of my x's though, I think. I want to get rid of my x's. So if I want my x's to go away, what I'm going to do is I'm going to have to multiply this first equation by 4. Because I want this to be multiplied by everything up here. What I'm going to multiply the bottom equation by is the top, by 3. But I need to do the opposite of one of them. So I'm going to make this one be negative. I could have made the top one be negative. It doesn't matter which, but one of them needs to be the opposite. So when I do that, let's see what we get. So distribute the 4. So that's going to be 12x plus 8y is equal to negative 4. And then down here on the bottom, I'm going to get negative 12x. Negative times negative is positive 15y. And then negative times negative is positive. This is going to be positive 96. And now when I add them, these cancel. 8 plus 15 is going to be 23y. And 96 and negative 4 is going to be 92. Again, x's went away. I have one equation, one variable. All I have to do is to divide by 23. 23's are going to cancel out, and y is equal to 4. So again, we have that y coordinate. I can pick either one of these equations to plug it into. 3x plus 2, well, we know y is equal to 4, is equal to negative 1. So 3x Now, I took this first one and plugged the y in to y. So 3x plus 8 is equal to negative 1. When we subtract 8 from both sides, 3x is equal to negative 9. And when we divide by 3, x is equal to negative 3.